So the vectorization toolkit from the previous lecture turns out to be quite useful in simplifying molecular tensors in the presence of symmetry and an application of symmetry to reduce the non-zero elements of the molecular tensor. Let me show you how this plays out. Let's first, before we can jump into nonlinear optics, review linear optics. So if I've got a vector in 3D space with some x, y, z coordinate right here, x, y, z, old, and I ask myself, if I know that my system has a sigma xz symmetry, in other words, it's identical upon reflection through the xz plane, then how do I apply symmetry? Well, what that's going to do, if I mirror plane reflect, then my new vector, oh, come on, I don't want that to be that color. There we go. My new vector is going to be pointing that way, and it's going to have a position of x minus y, z, because I've reflected about the xz. And that's my new coordinate system for that vector, that new x, y, z coordinates of that particular vector. So how do you think about this in terms of a symmetry operation? Well, I'm taking x goes into x, y goes into minus y, and z goes into z. So the transformation matrix corresponding to sigma xz 1, 0, 0, 0, negative 1, 0, 0, 0, 1. And that's my symmetry operation. How does this play out in terms of identifying the non-zero elements? Well, we kind of know already what's going to happen. If the system has mirror plane symmetry, then you can see that the y position must be 0. So that's going to be the final outcome. How do we get that based on this symmetry operation? Well, we consider the fact that if you apply a symmetry operation, if the system has that symmetry, then it must be unchanged. So we can figure out what the allowed symmetry elements are by adding I plus sigma xz and figuring out what survives this set of operations. Basically, I is doing nothing, and sigma xz is doing the symmetry operation. So that would be 1, 0, 0, 0, 1, 0. I'll put a 1 half in here too, so that it's all still normalized. 0, 0, 1 plus 1, 0, 0, 0, negative 1, 0, 0, 0, 1. And what do we see? We see that the x and the z components are unchanged, and the y must be 0 if a system has this symmetry operation. If a system has this symmetry. So that's how we can identify relationships between tensor elements and vectors and matrices. We'd love to do the same idea for matrices, except it turns out that you can't just set them equal to each other in this simple way. However, there is a route forward if we take advantage of vectorization. And the vectorized form gives us this expression for the old and new matrix elements. And it's just simply we generate that by a simple Kronecker product of the symmetry matrix with itself to expand it out. And as you can see, this is what you get, where there's zeros everywhere, and then it's just the diagonal elements that survive because we're starting out with a diagonal element for sigma. And these are the non-zero elements. And so if we add this plus the identity, which is 1s all the way down the diagonal, you're going to see that this one will stay, this one will go away, that one will go away, everything with a negative sign here will go away, and everything else will be retained. And those will be the elements of alpha that are symmetry allowed upon application of this symmetry operation. And that removes everything with a single y. Now we can sort of intuit this as well. We can intuit it because we knew from before that the symmetry operation takes x into x, y into negative y, and z into z. So we know just from the fact that we have a sign inversion there that anything with a single negative y, with a single y, should invert in sign upon application of the symmetry. And so we could have sort of guessed what this outcome was going to be for this particular symmetry operation without this more formal design. But we will see times where it's not quite as obvious, and having this formal architecture in place is advantageous. So again, we can take the same idea on to tensors, where it's not hard at all as long as we use the vectorized notation to just throw in another Kronecker product of the symmetry matrix. And then again, it's just adding that with the identity to determine which elements are non-zero. And as in the case of alpha, as well as mu, it'll be anything with a single non-zero y element, or an odd number more formally. So y will also disappear. will go away by application of symmetry. I won't bother writing all of those out because it's just big 27 set of numbers, and most of those are pretty straightforward. I will go through one explicit example for the C3 symmetry operation in which it's not quite as obvious what the outcome of that symmetry operation is going to be. So we already have the rotation matrix from a previous discussion. We can use that rotation matrix to understand what the symmetry operation does to the system. So if we have threefold symmetry, then that corresponds to a symmetry operation of 0 rotation, 2 pi divided by 3, 2 pi times 2/3, and then 2 pi back to 1, which gives us 0 rotation again. So it's 120-degree rotation each time, corresponding to threefold rotational symmetry. And we're rotating about the z-axis, and so the question is this is azimuthal rotation only, and we can use that azimuthal rotation matrix that was discussed in a previous presentation. So how does that play out in terms of the symmetry operations? Well, it's not necessarily really obvious, but if you go ahead and perform those symmetry operations for 120-degree rotations and then add I plus 120-degree rotated plus 240-degree rotation, this set of 27 squared numbers emerges. Most of these are zeros, but it's not too hard to look through this list and see the symmetry relationships that do emerge. And this is just one of many. You can see that for these 4 tensor elements, they all are, so this is the rotated here, and this is the input here. This is beta prime. And so you can see if we have C3 symmetry, then the XXX element must be equal and opposite to the XYY, YXY, and YYX. And this is just based on the application of the C3 symmetry operation. There's no other introduction of symmetry in order to satisfy this condition. And similarly, just by inspection of this table, you can come up with a whole bunch of additional symmetry equalities and symmetry relationships that come out of this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, the 9 really isn't a symmetry operation. So that is how we can take advantage of this architecture for application of symmetry to identify buried relationships between tensor elements in the presence of molecular symmetry.